Hello everyone, maybe we should get started. So today we have the pleasure to receive Professor Léon Koopmans, from Groningen. So I know Léon for quite a few years, so maybe 15 years when we started working together on strong dancing. But so Léon got his PhD in Groningen. It's working or in 2000, if I read well. And since you went in postdoc, in different postdocs in Caltech or STSCI, and came back to Europe, Netherlands, Groningen again as an assistant professor in 2004, and since you are now full professor there, with a lot of involvement in LOFAR and reionization business. This is the topic of today's talk, but also on lensing aspects, where these are the topics we work together on, particularly for Euclid, for kids, and the slacks in the early days. So today you're going to talk about LOFAR, and I think I'll leave you the speech.
Okay, thank you. So, well, first of all, it's a pleasure to be back. I think this is my, I don't know, 5th or 6th time here, I think, in the IAP. So it's always a pleasure to be here. So yeah, today is going to be completely different from yesterday's talk. So this is my other, the other half of my brain, as I said yesterday, reionization, and more recently also the cosmic dawn, and as I say here, right, I crossed out cosmic dawn, and I will say a little bit about the dark ages at the end of my talk, because we have an experiment now up in space behind the moon, taking data, right, at redshifts of the cosmic, of the dark ages. So this will be the focus of my talk, and in particular I will focus on how to sort of probe these eras in the first billion years of the universe using the 21 centimeter line of neutral hydrogen. And this is very, very difficult. There are many, many experiments trying to do this. We are leading one of these experiments. It's very, very hard, as I will show, but we're making steady progress. And of course, now I'm probably too far away from, let's see, yes. So maybe I should stand on this side then. So, so this is just one summary overview of cosmic history. And one thing I always like to emphasize is, right, so this is of course the CMB, and has been extremely well studied by, for example, Planck. Right, this is where the first stars, the first galaxies, sort of as we know them, appear around redshift 6. And then you have reionization, which is that period just before it. You have the cosmic dawn, and you have the dark ages. And to be honest, we know far less about this 1 billion years of the universe compared to what we know at this one slice in time from the cosmic microwave background. And this is really a treasure trove, right, of information in here if you are able to study this regime in neutral hydrogen. It has about 3 orders of magnitude more information in it in terms of sort of modes than the cosmic microwave background. But of course, right, later on you also are looking at galaxies, you're looking at the first stars, you're looking at the first black holes that form in this era. So we know more about recombination than about reionization, I always say. So this is, of course, the motivation for us to study this era here, because it puts down the foundation for everything that we see around us today.
How do you count these modes? Why do you say there's this order of magnitude difference?
So this is so if you actually count the number of independent modes that you can measure in the CMB just from the power spectrum. The statement is about the power spectrum. Then this of course is a 2-dimensional slice in time. This is a volume. If you count the independent modes in the power spectrum of this 3D volume in neutral hydrogen, it's 3 orders of magnitude larger. So that's the statement. Of course, that's not the only information. So what's the evidence for reionization? What do we know so far that is not related to the 21 centimeter line? And I will go through this very quickly. Of course, you have the cosmic microwave background, Thomson scattering, right, optical depth, which has been measured and puts a constraint on when reionization should be happening or should have happened, right? So if the universe, if reionization occurs at very high redshifts, the universe is very dense and the scattering, the Thomson scattering optical depth is very large. If reionization happens at lower redshifts, when the universe is already more expanded, the density of electrons is lower, the optical depth is lower. And this puts reionization at a, well, compared to, let's say, 15 years ago when people thought this would be at redshift 20, now with, right, improved measurements of the optical depth from Planck, this is now thought to happen around redshift 8. Right, so reionization should be, and of course this is an instantaneous reionization model more or less, right, but, and it's of course extended, but one should think of this, this sort of redshift when reionization is more or less halfway. Of course there is, this is also where it all started, right, with the Peterson effect, but if you look at high redshift quasars, right, at lower redshift quasars, let's say redshift 5.7, you see still a lot of transmission coming through. But as you go to the higher redshifts, you start seeing these very empty regions, and this is thought to be due to absorption by neutral hydrogen. Now, if you plot the optical depth then of the absorption as function of redshift, you see it go up very, very quickly. Now, of course, this is still a very, very small neutral fraction, but you see the tail of reionization occurring in front of you, and of course this will shoot through the roof very quickly. So that, right, that shows you that reionization is effectively ending at the redshift of 5, but some people even think there might be a tail to 6, and might even be a tail down to redshift of 5. If you look, for example, in this highest redshift quasar, then you can use the Lymanalpha damping wing, and you can do all kinds of fancy modeling of this spectrum and ask yourself, well, what's the neutral fraction here? And you're using the damping wing because if you actually use the Lymanalpha line itself, like in the Gunn-Peterson effect, and even a tiny, tiny, tiny neutral fraction will wipe out your signal completely. But if you go far into the damping wing of Lymanalpha, it's far less effective, so you're also much more sensitive to neutral fractions, which are much, much larger. And if you do that, then at the redshift 7.5, this is the probability distribution function of the neutral fraction, sort of right around the redshift, around the neutral fraction of 1/2. Maybe with a lower limit of like 0.2 or 0.3. So this suggests again, right, that at this redshift 7.5, 8, consistent with the optical depth, there is a considerable amount of neutral hydrogen at these redshifts. Similarly, the Lymanalpha luminosity function seems to drop very rapidly beyond redshift 6, and this is thought to be due to ionized bubbles, which are very small around these objects, and the Lymanalpha emission, once it reaches, let's say, the edges of this bubble, is not redshifted out of resonance yet, and therefore, if the bubble is too small, you won't even see the Lymanalpha emitter, even if it's there. So this is thought not to be evolution, but maybe more the fact that the bubbles, the ionized bubbles, are still too small. And again, that suggests that the medium is significantly neutral. And this is something else, of course. These are the galaxies that are now being found via dropout techniques or otherwise, even up to redshifts of 11 claimed. Some of them are lensed, right? And you see this incredibly rapid increase. Again, some of it is, of course, selection effects in the number of galaxies as you go to lower redshifts. So all of this suggests that reionization was sort of occurring around the redshift of 8 in a slightly extended period, was done by redshift 6. But of course, all of this information here that I just mentioned, and there are more, there's more information, is rather circumstantial, right? We are looking at the effects, right, on the neutral hydrogen, but we're not looking at the neutral hydrogen itself. right? The only evidence, and I'll come to that later on, at the moment might be from the EDGES experiment. So what do we expect to see, right? So these are the sort of a couple of slides summary of the observations of the epoch of reionization, and there are many more with ALMA, etc., which I haven't even shown. But what do you expect to see from this era in the 21 centimeter line itself? And that's summarized here, so, and there's a lot to learn from the neutral hydrogen 21 centimeter line. Of course, when you look at reionization, you will have the disappearance, of course, of this neutral hydrogen, but you also have IgM feedback. You have population 2 to population 3 to 2 transition. Of course, you have the first galaxies that we see around us today forming, and the emergence of the visible universe. And this is something that we in principle can probe, this redshift range, with current low-frequency radio interferometers. And I will focus on LOFAR shortly. If you go to higher redshifts, you get the appearance of the first stars, maybe the first black holes, right? You get the appearance of Lymanalpha UV radiation fields, which are heating and the X-rays, which are heating the medium itself. And something else, there are still an impact of these baryonic bulk flows that emerge after recombination. And if you go to even higher redshifts, to the dark ages, and recently we wrote a white paper on this for ESA to push for a space interferometer, you can really do all this fun, wonderful stuff you're doing with the cosmic microwave background, but then with a 21 centimeter line. So you're actually doing physics of, for example, dark matter, of gravity, the dark matter power spectrum evolution, etc. So this is really fundamental physics, but this is extremely hard to do. I mean, this is already hard, this is very hard. But I will show some recent first observations where we are attempting to observe this redshift range. So this is, right, Reionization. This is a movie already 10 years, more than 10 years ago, but I think it's still one of the most beautiful ones, sort of visualizing the reionization of the universe, right, where you have in high density regions galaxies and stars forming, right, with UV radiation ionizing these bubbles, right, and now currently we are trying to measure this statistically, but with the SKA we can start making these sort of cubes. Now, unfortunately, with SKA we can't rotate them like this, but right, we can actually go through a cube like this and image this process as it occurs. So that's right, something for the end of this decade or early coming decade. So at the moment, all experiments try to measure this statistically. So if you take a slice through such a box, right, and radio astronomers like to do things in temperature, in brightness temperature. So this is a temperature in millikelvin, right? And I'll come back to that in a moment. What does it mean? The signal is millikelvin. It's very, very faint, right? You might be able to see something like this if you make a slice through such a box as function of frequency, which is equivalent to redshift, right? And this is one spatial slice. So at the higher redshifts, at the lower frequencies, you have a fully neutral medium. You see it in absorption against the cosmic microwave background. And then as you go to lower redshifts, ionization starts occurring, these bubbles appear, and then reionization completes. So this is really the information in this evolution and these bubbles appearing and the temperature and the power spectra, right? That is where our astrophysical information is. Right, so this, right, in this temperature you have information both about the ionization, about the cosmology, about what I call the gastrophysics, let's say, mostly due to spin temperature fluctuations and peculiar velocities. So if I go back to this, right, in some sense we're measuring this brightness temperature field, and what we're trying to do is disentangle this information, the ionization, the cosmology, the astrophysics, and these peculiar velocities, right? And that's obviously not an easy thing to do. And what drives the spin temperature and the ionization, etc., and this, right, is mostly the underlying astrophysics of stars and black holes, AGN, etc. So coupling, right, these here to the underlying sources of reionization is by itself a very complicated process. Now, if you think about this two-dimensional brightness temperature map, right, in general, there are two things that we are doing to quantify this, but there are many more. But the first order things are to quantify it in terms of its average temperature against the CMB, right? That's what we call the global 21 centimeter signal. And you would get maybe something like this as function of frequency or redshift. So for most of the cosmic dawn, for example, this area here, you would see it in absorption, and later on you would see it in emission against the CMB. Right? And then depending on your models, of course, that global signal can change. Right? So this is, right, by measuring this shape, you will be able to say something about X-ray heating, Lymanalpha, emission, etc. Similarly, if you look at the power spectrum or the fluctuations of that field, on a particular scale, so K scale of 0.1, for example, there is a distinct change and evolution going on as function of redshift. So by measuring this, again, you can measure many of the properties of the underlying sources. And that is the first order goal of all the experiments currently going on, is to measure either this or that. And there are two different types of experiments, as I will explain in a moment. Right? And as I said, right, you can tie this to the underlying properties of the astrophysical sources, right? The first stars, X-ray binaries doing the heating, AGN, right? So, and you can describe that by these parameters here, and then you can ask yourself, well, what impact does it have? Right? So if you change those parameters, you will change not just the power spectrum here. This is just in one scale, so the variance on a particular scale, but it's in general the power spectrum. Also the global signal will change, right? So this brightness temperature map will change as you change the heating, the efficiency, ionization efficiency, mean free path, etc., and the spectrum of the heating, etc. So by measuring, right, these global signal and the power spectra, we hope to invert it and then learn something about the underlying astrophysics, and of course combine this with the information that we know from these other observations that I showed at the beginning. So the two ways of approaching measuring the 21 centimeter signal. So one is, as I mentioned already, by looking at the intensity fluctuations. So we look at this map and we look at the fluctuations on a given scale, right? This is the power spectrum. Now that's just one. You can go to bispectra, moment analysis, non-Gaussianity, etc. But the first order thing that we all aim for is simply measuring the variance on a couple of scales and do that as a function of a couple of redshifts. Right? I would be happy if we can reach that goal initially. Then we can think about all these other wonderful things. And this is what we're doing, for example, with LOFAR and what other people, and also with NenuFAR, one of the French interferometer. I'll talk about this at the end. And many other interferometers are aiming for this as well. The global average can be done in a much simpler way with a single dipole. Right? That is done, for example, by the EDGES team, by also groups in India, in the US, etc. And this is a space tripole system that I'm involved in, that I will show in the end as well, that is trying to do this from space. Okay, so, yes. So these are the big four interferometers that are attempting to do 21 centimeter signal measurements from the ground. Now paper is no longer, is decommissioned now. This is being changed into the HERA array, right? So this one is no longer observing. But the GMRT was the first one setting limits on the 21 centimeter power spectrum. MWA is the experiment in Western Australia, and LOFAR is the telescope in the Netherlands and within Europe that we are using. And that is the focus, again, of today's talk. Now, I want to show this here because there are maybe now glimpses of this 21 centimeter signal. Probably all of you have heard about the results from the EDGES collaboration, the EDGES team that found this signal, right? So now compare it to some of these theoretical signals. Now the thing you notice is, yes, it's more or less at redshift where we would expect it to be. The only difference being that this goes to roughly minus 200 and this goes to roughly minus 600. So it's about 2 to 3 times deeper than more or less any conventional model can predict. So there's still lots of questions about this, but I was in a meeting last week in India where they showed new results by a new instrument from the same team, but a scaled one, and this feature remains. Now there's still questions about how to subtract the foregrounds, but to me it starts to look believable that there is something there, but I would not fully trust yet how deep and what the shape is. So we're getting close as a community. So where are we with LOFAR, right? So I'll give you a status update on this now. So we've been doing this experiment. We started this in 2004, this key project. We have been collecting data since 2012. And several years ago, we published our first limits, and we have papers now submitted that I will show in a moment where we are publishing a much deeper new result. So these are our goals as a key science project on LOFAR to get the 21 centimeter signal, to measure power spectra. If we're lucky, get H1 absorption against bright radio sources. You have to be lucky here because these radio sources are unlikely to exist there. Of course, we can measure the variance and maybe, but I think I'm not too hopeful with LOFAR here, to measure the largest bubbles. But this is our first order, our first aim, to measure the power spectra of the 21 centimeter signal and then constrain these properties. Now, of course, this is not something I do by myself. This is some of the team members here in a meeting we had last year in May in Groningen. This is about half, probably about half of the people involved in the project. So it's about 25 people involved in this key science project. Of course, discounting the fact that LOFAR itself is a big machine being maintained by many, many people. Right? We are not running LOFAR, we're using LOFAR. So this is LOFAR for those living under a rock, right? I mean, you probably have all heard about it, and even in France, this was used to be the LOFAR superstation. Now it's NenuFAR, right? It's one of the stations, part of LOFAR, of the European long baselines, right? In Ireland, England, Sweden, Estonia, Poland, in Germany, so in France, and also in the Netherlands, and then in the near future in Italy as well. Now, most of the collecting area that is important for us is shown here in red. This is really what we are using most of the time to take our data and to do our calibration. We sometimes use these long baselines, for example, to make very high resolution observations of bright sources in our field that we want to subtract. But in general, these are the baselines that we are mostly interested in. And in fact, we are mostly interested even in the baselines that are very close to the center of the array, the inner 4 kilometers. They give us most of the surface brightness temperature of the 21 centimeter line, which peaks more or less around tenths of arc minutes. So tenths of arc minutes resolution, we get about 6 arc second resolution on the Dutch baselines, sub-arc second resolution on the European baselines. And on these baselines, we get tenths of arc minutes and degree. And also the UV coverage is very good. Surface brightness sensitivity is very good, especially with these inner stations here. In this inner 300 meters, we have 12 stations. Right? They give us most of the sensitivity. So we're using these stations here, these sort of boxes, 24 boxes, each with 4x4 dipoles. And then we cross-correlate all of these together also with these stations here, and that gives us the data that we are analyzing. So this is an observation of most of the sky taken with the overall LWA. The fields, unfortunately, is in purple here, but you can probably just see them. This is the North Celestial Pole. This is the field that we're observing with LOFAR. The reason being that the North Celestial Pole is there. It sits there all the time. We can see it all the time, so we can observe year round. And if we point there, the sky just rotates, so we don't need to track the sky. And this is actually quite a big advantage. And then we have another field, 3C196, with a bright calibrator in there. And that bright calibrator we can use to do bandpass calibration. But I will focus mostly on the North Celestial Pole. So this is another image of the North Celestial Pole that we made with the low band antenna of LOFAR by cross-correlating all the dipoles. So we can also make a northern sky image, let's say. And the NCP is here, and if you just rotate it here, then this is the NCP. This is the same image here made at higher frequency, so this looks much more like the field we're analyzing, but it's going much further out. So you see all these bright sources, diffuse emission in Stokes' eye, and this is actually the small area that we are analyzing, because we're analyzing something that is coming from the beamform data, and the primary beam of LOFAR is roughly this size here. So this is ultimately out of the entire sky, 4 by 4 degrees is the area that we analyze and it goes into our power spectra. Now, where are we in terms of data? We have, with LOFAR over the last 8 years, we have collected this amount of hours of data, about 3,300 hours of data and about 5 petabytes. So this is a lot of data. Right, so we have a big machine to process and store this. In parallel, we're also observing with ArtFAR, I'll come back to that. We have 500 hours, and we are starting now with NenuFAR, a key project. We have already collected 400 hours, and we'll get another 1,000 hours in the coming year with the new NenuFAR array, but at higher redshifts. Now, our main challenge in this project is, unlike the CMB, where your foregrounds are not your biggest enemy. I mean, they are an enemy, but not your biggest enemy. In 21 centimeter signal, coming back to these millikelvin signals, the foregrounds, the galactic foregrounds, are several hundred to several thousand Kelvin, depending on which frequency you observe. Now, on the same angular scales, let's say of half a degree, it's about a few Kelvin, and a few millikelvin for the 21 centimeter signal. So our 21 centimeter signal sits 3 orders of magnitude below the foregrounds. Right? Now that's a real enemy. Right? So we need to remove those galactic foregrounds, but we're lucky that the foregrounds are spectrally smooth, so if we get information in the frequency direction, we can subtract off that smooth galactic foreground, and the 21 centimeter signal is fluctuating. So if we make a model of the foregrounds, we can subtract it off without subtracting the 21 centimeter signal. At least that's the plan. But of course, there are other challenges. We have to deal with, this is an array where we do beamforming. Tiles can drop out, dipoles can drop out, your amplifiers can change. So your beam varies in all directions for all stations. There is RFI, of course, which you need to get rid of, and your bandpass is not always the same and not always smooth. And then ultimately you have the ionosphere. This is a good night, that's a bad night, right? So this kind of data we cannot use. We throw it, well, we don't throw it away, but we don't use it. And this happens about 20% of the time, 30 maybe. But 70% of the time it's really, really good quality data. So, as I said, we put everything in a power spectrum. That's ultimately the space that we're working in. So if you do that with all your foregrounds in there, and this is in cosmological units of K, but this is basically baseline length, so longer baselines, shorter baselines, and this is the Fourier transform of the frequency direction. Now, why can we do this? Because we have a 21 centimeter line. So every frequency corresponds to a redshift, every redshift corresponds to a co-moving distance, right? So if you Fourier transform, you get 1 over co-moving distance, which is a K-scale, which we call K-parallel. So this is effectively the Fourier transform, right, or the power spectrum of your 21 centimeter signal if there were no foregrounds. Now these foregrounds, they live down here, because they're spectrally smooth, so they only have very large scales. This stuff here is leakage because of the instrument. I'll not go into it, but it goes maximally up to this line, and then above it we call EOR window. Now many experiments, they try just to look here. We're also trying to look here by removing the foregrounds. That makes it especially hard. But this is where most of your information actually is. So if you decide to build an instrument and only use this, you're effectively throwing away 90% of your collecting area, which I don't think is a smart thing to do. Now we have set up over the last decade a quite sophisticated pipeline to process this data. We have developed calibration software, RFI mitigation, imaging, etc. So this is just a quick overview of that. We run this software on a GPU cluster in Groningen with about 132 K40 GPUs. So it's a very, very powerful machine. But still, it takes one night of processing, one night of data processing takes about a week on such a machine. So this is still, and we're talking about maybe 5 to 10 terabytes of data. So where are we, or where were we? In 2017, based on the data, we published one night of data after a lot of tests and things we thought were correct then. And we came then with the deepest 21 centimeter power spectrum upper limit at redshift 8 to 10. Sorry, this is typo here. So, but still many, many orders of magnitude away from the 21 centimeter the expected 21 centimeter signal. We also recently published at much higher redshift limit, but again, it's only interesting to exclude what we call exotic models. It's not even close to the prediction, but you can't expect that in a few hours of data. So just to put this in perspective, right? So these are now at a given K scale of 0.1. So all these experiments are now sort of normalized to this scale. 2 sigma upper limits in millikelvin squared, and these are sort of models, maybe this one is the more realistic one now, where the expected signal is, right? And this is where the upper limits are. And this is our upper limits here in yellow from 2017. Now this is not where we are now, I will show that in a moment. So this is where we are, and you can see we're still several orders of magnitude away from any detection. But we only looked at 1% of our data, so it's maybe not so surprising. So new results. So we submitted just before Christmas, so if the referee is in the audience, thank you for reading our papers over Christmas, because just after Christmas or just after New Year we got our referee report, which is very, very good, so we resubmitted already. So we expect at least this paper here on the new upper limit to appear in the coming months or so. And we also submitted a theory paper where we interpret this in terms of the IGM properties, and I will not go further into that here. So what did we do in this new paper? Why have we made such an incredible progress since the previous observations? The previous analysis, and that is mostly in the direction-dependent calibration. So you think of LOFAR, right? You have stations, but each station is slightly different. So the way you look at the sky is slightly distorted for each of them. And then you cross-correlate them, and if you do that, you get slight distortions as function of direction in the sky. And you need to solve for that. If you don't do that, those hundreds of kelvins and very bright sources, they scatter power all over the place, and they will swamp your 21 centimeter signal. So we developed a very a calibration model where we solve for the primary beam for all stations, 63 of them in 122 directions, every couple of minutes, and for all frequencies, right? So you can imagine why we need that GPU cluster. It's computation very expensive. So what we do is with those calibrations that I'll come back to in a moment, we take out all these bright sources so that we empty it out as far as we can, and then in the next step we use a different Gaussian process regression to take out the remaining foregrounds. So we basically cluster sources in the sky in different groups. roughly based on their brightness. And then each of these has a different full Stokes-Jones matrix correction in that direction. Now, I'm not going to explain what it is, but it's basically a correction to the sensitivity of your station in a particular direction. So we have this, but we have it basically for all stations in every couple of minutes and all frequencies. So 122 directions we solve. We solve basically this equation. Again, don't bother too much. This is your usual chi-squared, right, fitting your model to the data. But we enforce spectral smoothness, and this is where we made most of the gains in the past years. We enforce spectral smoothness on our solutions. We know the instrument is spectrally smooth, but if we don't enforce it, because of the model being incomplete, we get all kinds of leakage, and this is now very well known in the community. So you can overcome this by adding these extra, basically Lagrange terms to your solutions and forcing your solutions to lie on a smooth curve. And that has really improved our calibration drastically by an order of magnitude in noise. So another thing that happened because of this is that whereas in 2017 our processing didn't suppress the signal, it did enhance the signal, because if you fit something or you're overfitting, let's say we are not fitting any baselines on this side, we're only fitting baselines on this side, and then we predict what it is on this side. That is like you're interpolating, and an interpolation gives you an excess noise. This is a very well-known thing in signal processing. So this is actually what we observe. We saw that the signal here is suppressed and the signal here was enhanced. So that's why in 2017, even though we knew we were not suppressing the signal, we were adding extra noise to our solution. That's not good. After we introduced this extra Lagrange term here, now we can see this is 1. It should all in principle be 1. Then it's good. Right? So more than 1 here is excess and less than 1 is suppression. Now you see it's basically all yellow. So we now know that we're not suppressing our signal and we're also not adding additional noise. This is all due to this extra term here. So that's good. So this is our field then zoomed in. This is actually the model just to show you for clarity. It looks a bit nicer. Right? This is when you actually subtract them off, and then if you change the dynamic range here, this is 100 in terms of Janskis. So now if you just change the dynamic range, you can see that now if you subtract everything off, you get effectively confusion limited images. So here we cannot really say anymore what's a source and what's not a source. It's all blending together. So we need a different technique to remove this. And we do that with so-called Gaussian process regression. It's another technique that we developed. So together with spectral smoothness enforced on our solutions, we are also effectively modeling the foregrounds in a much more sophisticated way than we did in 2017. Now I will not go into the details, but the Gaussian process is basically describing your foreground, your 21 centimeter signal, and instrumental effects, as the name says, as a Gaussian process. It's quite powerful, and you can use the statistical properties of those signals, for example, the fact that your foregrounds are spectrally smooth on very large scales. You can use that and build that into these sort of covariance kernels, and then you can filter out the foregrounds. Now we've proven.
Can you show the previous image, please?
Yes, this one here.
Why is there a gradient towards this galactic center? Is there more stuff in
This is the North Celestial Pole,
yes.
and the fact that it drops off, you see it here. That this is the primary beam of your station. So this is the sensitivity pattern of your. This is the null. It's basically like an Airy pattern. So you're most sensitive here. That's why we only analyze this inner bit. And this, the fact that you don't see much here is not because there is not much there. It's just that your beam drops off and then goes like this. So it's an instrumental sensitivity. So this Gaussian process we've shown on simulations to work. This was an SKA simulation, but it's very similar for LOFAR. And we show this is the truth here. the orange line, and if you, of course, depending on the signal to noise, right, you actually get an unbiased estimator of the truth in such a Gaussian process. So that's good. We've shown that it actually works. We tested this many times, so we're quite confident that this is okay. So what does it do on real data? So this is, now again, this is a spatial slice and a frequency slice. This is our data, so we see the sources in here, but it's more or less confusion limited. This is the Gaussian process regression model, and if we subtract it, we basically get something that looks like noise. Looks a bit squarish here, but that's just because of the resolution. So Gaussian process, this is our original foregrounds. When we subtract all the point sources with direction dependent calibration, we get here, and after Gaussian process regression, we get here. Now you can see that this is still has some excess noise, so we're not at the thermal noise yet, but this is much, much better than what we did previously in 2017. We will be up here somewhere in the same amount of time. So this is now our power spectrum with the foregrounds, and then after Gaussian process regression, this is the cube that we hope has just noise and 21 centimeter signal in it. And this is the ones that we analyze. So we've done this for 12 nights, and we picked the best 10. 2 of them have a slightly larger noise. So we combine these 10 out of 12 nights. We look at cross correlations. I will not go into this further. I will just go immediately to the results. So this is where our foregrounds are, and this is where we are now in terms of the power spectrum from this data. So you can see how many orders of magnitude in dynamic range we have taken out the foregrounds. And this is where we were in 2017. So we've gained an order of magnitude in depth. So our power spectra are now at the same K-scale, a factor of 10 deeper. So to update this plot, right, we have moved this point here now down by a factor of 10. So we're still 2 orders of magnitude away, but don't forget we are only analyzing 5% of our data. So, and based on what we know that we're not at the thermal noise, we know we can move this point here still, based on the same data, and then we still have a factor of 20 more data, so we should be able to reach this level using 1,000 hours of data. And given that we have 2,200 hours, we should be able to reach this level. That's our forecast. So this is where we are now. So I don't know how much time I have left. Probably 5 minutes. So let me skip over some of this very quickly. This is observations that we have done with the LOFAR LBA system as a reaction to this edges signal, because if this is true, then also the fluctuation should be much, much larger. And then LOFAR would be, at the low frequencies would suddenly become sensitive enough to see this. So this is a project that my former student Léon is carrying out. He's now postdoc in Judd Bauman's edges team, where we cross-correlate all the individual dipoles in the inner center of LOFAR. So we get very, very good UV coverage, and we get all sky sensitivity. And
so the edges signal is at a much lower frequency?
Yeah, it's at the lower frequency. It's around the redshift, about the frequency of 75 megahertz. So it's about half of what we...
FM radio?
Sorry?
FM radio?
It's below the FM, yes. Otherwise, yeah. You have to go to Western Australia for that. So this is, again, this image that we see with the system. It's more or less all sky. This is just 15 minutes of data. These are power spectra before and after GPR, so this Gaussian process regression. And this is the power spectrum that we are about to publish in the next couple of weeks. So if we look again, where is it? Well, it's up there. Right? This is many, many orders of magnitude away from standard signals, but there are many non-standard models predicted based on that edges signal that we should be able to reach with our data. We have 500 hours of data, and this is only, well, 14 hours of, or 1.5 hour of data, 2 hours of data. Okay. Okay, so since I have only, I'll go skip over a couple of things, but I will not skip over NenuFAR because that's of course the array in the French backyard, let's say, just south of here, a couple of hours, which is the most sensitive low-frequency array currently operating in the world. So we are having a key science project on that to look at the cosmic dawn, so at these redshift of the edges band, but even lower with this instrument in the coming year. And we have already started observing. Let me just go over this quickly. We have already started observing since last year in a sort of limited mode, but in stage 2, which will start soon, with the correlator, we will get 1,000 hours, and we should be able to reach sensitivity levels below where nominal models predict the 21 centimeter signal to be. So actually, France has the most sensitive cosmic dawn experiment currently in the world. Tell that to the people from SKA. If you try to join SKA, you have the most powerful instrument. So this is just the images or at some frequencies. It's very preliminary work. Right, you're reaching the thermal noise level. So that all looks quite good. So I'll skip over here on SKA because I want to end with why I crossed out Cosmic Dawn and added the Dark Ages in my title. So let me just quickly go over this here. Okay. So the last thing in the last few minutes I would like to end with is with an experiment that I'm involved in as one of the science team members in the Netherlands, one of the Dutch co-PIs of the Netherlands-China Low Frequency Explorer NCLE. So this is an experiment that happened very, very quickly because the Chinese were sending, and they are sending, of course, a lot of missions to the moon. And they had space on one of their systems to launch a very small experiment. So effectively, the Dutch started collaborating with the Chinese to put a low-frequency tripole system on the relay satellite of the Chang'e 4 mission, which you probably have all seen in the news last year. So, okay, so these are all the contributing members. So this is our king here with the Chinese president, I guess. I don't know what, not sure what you can call him these days. But well, this is on YouTube, right? I have to be careful. Right, so, well, this is the moon, of course. So the idea of this mission is that, right, that there is a mission to the moon, but there is a relay satellite behind it. That relay satellite is in L2 that looks to the moon, but it also looks at the Earth. So signals from the backside of the moon go to the relay satellite and then to Earth and the other way around. And on this relay satellite is a tripole, 5-meter long receivers. And then, of course, after that, the Chinese sent a lander to the moon and also orbiters. Right? So this is a very complicated mission. But the relay satellite is there to communicate from the backside of the moon back. And on that relay satellite is where this experiment is mounted. Now, just in terms of sensitivity, right, the ionosphere doesn't allow us to go to frequencies from the Earth, so that's why you have to go into space. In principle, in the mission lifetime, we should be able to reach sensitivity levels that reach to the dark ages. So that makes it very interesting. Of course, this is all done very quickly. This is not optimized, right? We look at this as a proof of principle, a pilot project. So this is the instruments, right? Digital receivers, amplifiers that are all there now in L2 behind the moon. And then these are the antennas, right? So if you have these tape measures, you know, the ones you roll out and so on, that's like this. So this is a rolled up receiver, and it rolls out 5 meters. I'll show that in a moment. So this is how everything is put together. This is how fast we work in the Netherlands. This is you see the tripoles going out here. This is anti-gravity, these balloons. And this is why you wished you didn't call your company ISIS. So, but unfortunately, this is a commercial company that builds instruments for space. So this was just to test the system, but I mean, they're very strong. These are carbon fiber partly, so they don't buckle easily, but just to make sure they put these balloons on there. Right, this is it mounted on the relay satellite here. This is the dish that points back to the Earth when it unfolds. Right, this is the tripole sticking out slightly, right, carbon fiber here. This is the launch in 2018, I think. And this was then the lander for the moon that happened last year. Right, so now then the surprise came. Right, this is not where the tripole is, but if you look at this, this is the lander. The Chinese decided to put another tripole on the lander itself as well. So there's also observations being done from the lunar surface. Right. So now this is it unfolding. Of course, this is right, artist impression, but this image is very exciting. So this is now the instrument in L2 behind the moon. So this is the moon. This is the Earth. So this is a camera on the back side, right? So it points at the moon and the Earth. So this is one of those wonderful images where you see the moon and the Earth simultaneously, and our instrument, NCLE, here. So it's now been rolled out, right? So this is what it looked like. It's been rolled out. And this is what I got at 3 a.m. last night. So this is, of course, very preliminary data. So this, don't look at this too much. This is actually some data that are being played with at the moment. So that's so there is an instrument behind the moon that can, in principle, cover frequencies here of the dark ages. So that's why we're super excited to have this as a pilot project. We don't think that this will maybe get there, but it will certainly tell us a lot about the environment around the moon. So that brings me to the general summary. So I hope I've convinced you that the 21 centimeter signal from the reionization, cosmic dawn, and dark ages is a very promising and unique probe of this first billion years. There are many ongoing and planned global and interferometric experiments. Right? They're extremely difficult, as I've shown you. We're all still several orders of magnitude away from a detection, but we all have only looked at about 1 or 2% of our data. There's steady progress, but it still requires long-term investments. Right? There are now also these first space-based missions. Right? We are finding maybe the first hints of a 21 centimeter signal from global experiments, edges. I'm very excited about this. It's deeper than we thought, but I think there are still issues to be solved there, but it looks very convincing. With LOFAR, we now have the deepest limits at these redshifts. And for the future, I think what is very promising is these updates to edges, other experiments for the global signal. So I think in the coming years, this global 21 centimeter signal, that will be found. I have no doubt about it. And if it's not found, we can rewrite all our textbooks. But I mean, that's going to be found. So I think also in the coming years, we will push with these current instruments very, very close to the 21 centimeter signal. Of course, nature gives what nature gives. So if nature makes a signal weaker, maybe we don't reach it. If it makes it stronger, we get a good signal to noise, right? So it's a detection experiment. Now, there's a lot of things already on the road. Of course, in your backyard and in my backyard, NenuFAR is the most powerful cosmic dawn 21 centimeter experiment. But HERA and SKA are also coming in the next few years. And especially with SKA, one can image the 21 centimeter signal. And then, of course, the ultimate dream would be to go for the dark ages, first for the global signal, and then in this white paper, and Joe was also involved in writing it and initiating this, is to have a space interferometer that can actually get the power spectrum of the dark ages and do all that wonderful fundamental physics that people are doing with the cosmic microwave background as well. And I'd like to stop here. Thank you.
Thanks, Léon, for the nice talk. Questions?
Could you, the Chinese NCLE experiment looks very intriguing, but it seems to be just an experimental demonstration that one can do something at very low frequencies. Could you comment on what they're planning to do next to actually do something which will get science from 30
yes,
megahertz?
So yeah, this was almost, so just to put things in perspective, right, this, of course, the Chinese will not tell you how much this costs, but I'm sure it's billions and billions of euros to put it up there. The NCLE experiment was done roughly in a year. To piggyback on it, of order 1.5 million euros. So it was done very quickly. Of course, it's not been designed to do something necessarily. You're on the relay satellite, it has RFI, you could see it. So there are discussions now between the team and the Chinese to actually in, I think it was Chang'e 7, so they're already planning quite far ahead, to make an RFI-free platform for an experiment like this. So that means that basically based on the experience here, they will start designing a new platform in Chang'e 7 that will go to the moon, and that will have a, or that's the discussion, that could have an NCLE 2 on it, and that will be much better designed for an experiment like this. So that the spectra will be looking much cleaner. So this is the discussion. So that's why I said it's a pilot. We're learning. We want to see what's going on. We see how much we can squeeze out of this. It's going to be much easier, for example, at the edges frequencies, because it's much more sensitive, but the dark age is going to be tough with this experiment. But there are discussions ongoing.
The time scale is what for this optimal project in Series 7?
I think, but don't quote me on it necessarily, because you never know, but the Chinese are, I mean, they're sometimes ahead of their schedule. I think the idea would be in the early 2020, so in 2 or 3 years. So this is not going to be end of the decade. This is, they want to go as quickly to the moon as possible and even put people there, but this is all put in that context.
Also about the NCLE, could you say something about, so recently the news has been that I mean, as you've shown, that you've started extending these poles, but they don't seem to be fully extended yet. What are the updates there? What are the prospects? And also, could you say what you expect to learn, particularly about the EDGES results from NCLE?
So yes, they are, so these tripoles, so they're basically 3, right? So one of them is fully extended, the other ones are not fully extended. They're actually at slightly shorter extension. So that actually, strangely enough, one of the discussions we had early last year in China is why don't we roll them out to maybe 1 meter, 2.5 meters, because your sensitivity to the higher frequencies becomes larger. So it's true that we now have a system maybe, because there's always a risk in these things, right? If you actually start it again to roll it out, whether that actually will damage the pole or not. So we don't want to take too many risks there. So we're basically taking the data with the extensions of the poles there are currently, which means that the shorter ones actually have more sensitivity to higher frequencies. Now, originally 5 meters is certainly, if I go back to, maybe I can go quickly back to this here. So this is, right, 5 meters is sort of maximizes sensitivity here, but not at these frequencies. You can see the sensitivity is far less here than it is here, and that is just because, right, the wavelength there is far less than 5 meters, so you're not optimal. But with a shorter dipole, if you go to, let's say, 1.5 meters, then actually your most sensitivity will be roughly here. So we expect this shorter, well, monopoles in this case, to have more sensitivity here than shown in this plot. So in that sense, you can think of it, yes, it's maybe right, an advantage of a disadvantage, let's say. If it didn't roll out completely, it actually means your this sensitivity curve is shifting in that direction. So, yeah.
Léon,
yes.
You have removed completely the RFI, but I was wondering, since you have several orders of magnitude, Are you sure you have not small residuals that bring you some noise?
Yeah, so this is, as I said, this is just test data. So there are techniques developed how you can filter out this RFI internally within the system. So yeah, we have to be careful that we are not leaving any RFI behind. Let me just go and. But this is all very, very fresh, so I cannot comment on. Oh, sorry, this is a bit slow. Right. So yes, that could be right. That some of this stuff here, it's very narrow. Right. That, of course, right, some of this is left behind, but if you just take out the very narrow lines in between, you will still have sensitivity. I mean, you can't really see it in this plot, but you can see that they are, right, this sort of very regular pattern. And this is basically all internal electronics RFI from the system. And of course, right, this is, it's being piggybacking on the relay satellite, which was not designed for an experiment like this.
Okay, so one last question.
Yeah. Could you come back to the edge signal? You say there are some problems with the interpretation, with the depth of the signal. What are the possibilities? A problem with background subtraction or what?
Yeah, so if you take their signal, you still have to model the foregrounds, and of course there could also still be instrumental effects. So if you model it in the way they do, which is just a 21 centimeter signal plus foregrounds, then this is what you get. But there have been other papers that say there is actually, it looks like there is a periodic ripple in the signal, and if you take that along in the model, then this could come, for example, from the cable, going from the electronics to the receiver. Then the 21 centimeter signal actually is much more in the regime of what these astrophysical models predict. Now what they did is, first of all, they showed this in India last week. If you take their instrument and they built a new one, which is actually smaller, if this is an instrument, if it actually comes from the receiver, this feature would shift around in frequency, and it doesn't. It still sits there, it looks exactly the same. So that tells you it's not some strange thing in the receiver. It could still be in the cable. So they're building an Edges 3 where the cable is taken out. They put everything inside, and they'll deploy that in the coming year. But the fact that they've done now an infinite number of tests and they cannot get rid of this feature. So I believe there is something there. I just don't believe yet that they have been able to separate, let's say, the foregrounds from the actual signal and the instrumental effects properly. So I think that is where they're going to work on most by completely redesigned their receiver. That should get rid of all of these effects. And I suspect they will find the signal then. That's my... I was much more, let's say, less hopeful when this came out. We put in, this came out a week before the LOFAR deadline. We then put in a proposal for 500 hours on ACE, just gambling on it. It's okay, if it's real, we'll go for it. But I wasn't super hopeful. But now with these new results, I'm quite hopeful there is something there. It just needs somewhat better analysis, I think, still. Yeah.
Okay, so no more questions. So let's thank again, Léon.